Hello, my name is Pete Zuzek from Zuzek Inc., and I'd like to present some slides to you today on the Maitland Valley Conservation Authority Coastal Hazard Mapping Update, and specifically dealing with the erosion hazard limit for this video. I'd like to acknowledge our partners with this work, including SJL Engineering and DHI. A significant portion of the study area is comprised of eroding bluff shorelines. These shorelines consist of materials that are highly erodible during storm action and waves. And we see a couple examples on the screen below. The one on the left is north of Goderich, the one on the right is south. Slide 3 presents a three-dimensional model of these bluffs to the north of Goderich. We see two important features on the map on the top panel. The top of bluff, which is the red line, and then the toe of the bluff, which is the blue. This area featured a substantial slope failure that was captured in the photograph on October 8th, 2021. We can see from the side view here that a large portion of this bluff material broke away and slumped into the lake. These trees at one point were growing up on the top of the bluff. One of the tasks we've been working on is quantifying at what rate these bluffs have been eroding historically. And in the example on slide 4, which is in the northern portion of the study area, the red dot, we have three sequences of historical shoreline position information: the 1930 top of bluff, 1966, and 2021. On the left-hand panel here, we're showing 1930 to 1966. The statistics here tell us that the average rate of recession was 0.16 meters per year with a standard deviation of 0.07, which measures the variability or the variance in the data and giving us a combined rate of 0.24 meters per year. When we compare 1966 to 2021, on the photo on the far right, we see again measurements. The white lines are the erosion transect measurements, and they are capturing the rate of change in that top of bank position. Here the rates have accelerated in the recent past to an average rate of 0.31 with a standard deviation of 0.8 to give us a combined rate of 0.38 meters per year. Slide 5 highlights the implications of this long-term recession process on our buildings and infrastructure. In the top, we have the 1930s line, 1966, and then 2020 in red. And we can see how that retreating bluff is getting closer to the infrastructure, to the buildings, and causing the associated risks for those locations being that close to the eroding feature. The bottom images are oblique photographs that were taken more recently, May 2017, 2021, and 2022. And we can see how the changing slope conditions are responding to the rising lake levels during that period. The materials are starting to become unstable in the May 2017 image. We have this notching and oversteepening of the bluff in July 2021. And then following that, there was this very large mass slope failure that resulted in the retreat of the bluff and getting very close to the proximity of the existing home. We've also been measuring changes in the gullies or the ravines that bisect the shoreline and deliver water to the lake. In the image below, the blue line corresponds to the top of the gully feature in 1930. And then fast forward to 2021 is the red line. As we can see that these gully walls, the side walls, are retreating over time. The combined rate is 0.13 meters per year. Similar type of information here south of Goderich now. The red dot is the location. We're looking at changes in that top of bank feature from 1977 to 2021. The white transects are our measurement locations, and the statistics here tell us that the long-term rate of retreat is 0.28 meters per year with a standard deviation of 0.16 for a combined recession rate of 0.44 meters per year. We're fortunate to have very detailed measurements of the land or the terrain in this study area. This information is referred to as LIDAR data, and the contours of elevation are shown in white on the slide 8. We can see that they have a very steep bank slope here, and then much flatter tablelands where the homes are typically located. And again, these two important features that we're monitoring: the toe of the bluff in the blue, and the red is the top of the bank. One of the observations we've been able to make throughout this work is how the differences in vegetative cover are influencing the shape and the morphology of the eroding bluffs. In the top photograph, where we have agriculture quite close to the edge of the bluffs, it's generally much steeper, with the slope of the bluffs featuring very little to no vegetation. And then if we look at the bottom panel of the map here on slide 9, you see that a much denser vegetative cover across the bluffs, and they're also generally much flatter or feature a gentler slope and are more stable when we have that vegetation present. Another important part of our technical work has been looking at changes in ice cover on Lake Huron over time. The map on the left-hand side is a gridded product, a government data set that tracks the changes in the ice cover throughout the winter season on Lake Huron. The red colors are locations where the gridded cell data is telling us we have 50 to 100% ice cover, transitioning to these yellow areas where the coverage is thinner at 11 to 30% of the open lake area. On the right-hand side is just another sample of the type of data sets that we have to do this analysis, and this is the actual raw satellite scene. We've got 10 days past since the gridded product from the government. Looking at this raw scene, we can see that the ice is quite a bit diminished here by March 18th, 1985, and it's limited to a narrow band along the shoreline, the white area showing up in the image. Next slide, I'm going to highlight some of the results at these 4 locations to the south of Goderich. Looking at the long period of record with this government data, we're capturing 2 time periods, 2 10-year periods where things are quite different on the amount of ice cover at those 4 locations, 0.9 to 12. These are corresponding to the different bars for the temporal periods. 77, 78, these are the winter seasons, and the number of days of ice cover at those points on the y-axis here. We look at this historical period from 77 to 86, we're generally in the range of 90 to 100 days of ice cover going back to those cold winter periods. If we look at the last 10 years of data, there's been quite a substantial reduction in ice cover, on average 30, 40 days, sometimes some seasons very little ice cover, as in 2012. And then we have a couple exceptions here with 2014, 2015, which were years heavily influenced by strong polar vortex events, where the jet stream is allowing the cold Arctic air to come south, and still has a fairly substantial amount of ice cover. But in general, overall, the trend has been a reduction in ice cover on Lake Huron over time in front of the Goderich shoreline and the shoreline throughout the Maitland Valley study area. Looking at all of the climate change forecast information, this trend is projected to continue. As our air and our lake temperatures continue to rise in the future during the winter period, we expect to see even less ice on the lake, and potentially going to years of almost ice-free conditions by late century. The graphic here is from a publication from Michigan Tech University, and they're projecting the continued reduction in the number of days. So these would be 10, 30, 40, 50 less days of ice in the future at both the mid-century period and then the late century period. So if we look at the most extreme warming case here for Lake Huron, we could see in portions of Lake Huron up to 40 or 50 days less ice cover by the end of the century. Slide 13 highlights some of the work we've been doing to look at the implication of losing our ice cover in the future as our atmosphere and our lake continues to warm. We've used some computer technology to simulate the actual historical waves throughout the study area with the actual ice cover conditions. Then we redo that simulation by removing all of the historical ice cover and calculate the difference in the amount of energy, the waves that are striking and reaching the shoreline and resulting in erosion. These bar charts are from comparing those two simulations from the north end of the site, moving south through Goderich, and then ultimately to the southern limit of the study area. The key takeaway here is that by taking the ice out of the simulation, the overall amount of energy that would have struck the shoreline historically was an increase of 35%. And that's significant because 35% more energy means recession rates are going to increase in the historically and in the future at a similar rate, 35%. As we generate the hazard mapping, which we'll discuss in the coming slides, we are then required to increase the historical recession rates to account for this ongoing reduction in ice cover in the future. We've increased the historical recession rates by 20% over the next 100 years to account for the impacts of climate change. Slide 14 explains the methodology, provincial methodology that we follow to map the erosion hazard limit. It's important first to note that this is based on a 100-year planning horizon. We have to map where these shorelines will be 100 years from now. We also are using the climate change recession rate, as I mentioned in the previous slide, where the historical rates are being increased by 20% to account for the continued loss of ice cover on Lake Huron. And the methodology includes this 3-to-1 horizontal to vertical setback to account for the stable slope. And that's shown here in the schematic diagram where we are assuming that it requires a distance of 3 along the x-axis and 1 on the y to have a stable slope orientation, and then the erosion of the toe in the future for the 100-year erosion allowance. That gives us a location on the top of the bank where the bluff could be in 100 years, and that corresponds to the red line shown on the 3D image here. So that is the combination of 100 years of erosion in the future plus the stable slope allowance. It's also important to note that the conservation authorities can add up to 15 meters of additional allowance to define their regulated area. We've applied this methodology throughout the study area from Amberley in the north all the way to the south boundary of the Conservation Authority, and we've created a series of three-dimensional videos, fly-throughs of the shoreline, where we've taken the buildings and we've color shaded them, and we're overlaying both the flooding hazard and the erosion hazard on these maps to show you where these new hazard limits are with respect to the lands in the study area and potentially with respect to your properties. So I encourage you to go to the project website where you found this video and select the one of interest, and you can play back that video to see the erosion hazard mapping in 3D as we fly from north to south along the shoreline. Please refer to the Maitland Valley Conservation Authority website for additional details on the updated hazard mapping. Thank you for listening.